sense. So here is a summary table that just compares these two, basically looking at osmolarity, a definition of what that is, and how the solute concentration would differ based upon our physiology. So our physiology is comfortable at 300 milliosmoles. And so we can think about hyper or hypo depending on the difference from that number. And then tonicity, looking at only the impermeate solutes, and again, how that would differ, hyper versus hyper. Hypo versus hyper, excuse me. All right. So if we look at these two scenarios, just to practice applying this, we've got a 300 milliosmoles on the inside of this solution, 150 on the outside. So as water begins to move according to its concentration gradient, we're going to have water move in what direction? Who can predict what direction the water will move to result in this scenario on the right? Where is the water at higher concentration and where is it at lower concentration, and where will it move? Excellent, thank you. Yep, so it's going to move into the cell. That is perfectly correct. If we think about the gradient that's created here, higher concentration out here, 150 is the osmolarity, lower water concentration in here, 300 is the osmolarity, and so water will move into the cell to equalize that osmolarity, and then the cell will swell. What about the scenario on B? Lower solute concentration, there's an osmolarity of 300 inside the cell. Outside the cell has a higher solute or lower water concentration. There's an osmolarity of 600. And so what direction does water move to give us this scenario on the right? Outside the cell, excellent. That is correct, thank you. So this water will move from the inside of the cell to the outside of the cell in the opposite direction, right? And you really want to not just think about the opposite, but think about reasoning through that, right? So it's going from a high water concentration inside to a low water concentration, and then that will allow the cell to crumple, and that will equalize the osmolarity. All right, excellent. Let's go on to introduce learning objective 2. Explain in general terms how the polarity of epithelial cells enables them to absorb or secrete materials. So here we're going to look a little bit at epithelia, which for some reason is one of my favorite topics. I love thinking about the cells that line all of our body cavities. So the epithelia is a very unique type of cell in the body. It is basically all of our lining structures. Think about your skin, that is all epithelia. All of your internal body cavities, your GI tract, it's all lined with epithelial cells, the inside of your bladder, your reproductive tract, your respiratory tract, all of your glands, right? So your thyroid gland, your pancreas, your liver, which is the largest gland in the body, your pituitary gland, the brain. All of your glands throughout the body are also made of epithelial cells. So epithelial cells can look very differently. They can be tall cells that have a lot of secretory function. They can be very flat cells that allow for absorption of oxygen, nutrients, etc. And so they are a unique type of tissue and cell that allow for transport across certain membranes. Now they're going to have two different surfaces, so they're going to have some polarity here. They're going to have an apical surface, which is at the top of the cell, and then they're going to have a basolateral membrane, which is at the bottom of the cell. Okay, so we can begin to think about this polarity, right, the top versus the bottom, when we think about these epithelia. The top or apical surface will usually face the lumen of that cavity. So think about this being your GI tract. Food comes moving through this surface. And so in order to get that nutrient, right, the biomolecules, the glucose from the food that we're eating, it's going to have to go through the apical surface of this membrane, and then it's going to have to get through the basolateral surface and then into the bloodstream. So that is really going to help us think about the direction of transport based on the polarity of these cells. Now, these cells are going to be adhered to each other by tight junctions. These junctions are going to ensure that there's no paracellular transport, otherwise known as leaking, right? We don't want anything to leak in between the sides of these cells. That can result in things like leaky gut syndrome, where things can just kind of move in between if these junctions are not very well secure. So tight junctions really help to adhere these two cells together and prevent any of that leakage in between. As far as thinking about the different sides of the cell, so if we look at the apical surface, molecules can get in through leak channels. So we talked about some of these leak channels earlier in part 2. We looked at sodium, for example, where sodium can move according to its passive gradient, right? Represented by the green arrow here, from a place of high concentration in the ECF to a place of low concentration in, a place of high concentration, the ECF, that was correct, I apologize, to a place of low sodium concentration in the ICF. So sodium leaks in freely, and then on the basolateral surface of the membrane, we have the sodium-potassium pump. And we described this pump earlier as well, but now we want to talk about where that pump is on the cell membrane. So on the opposite end of the cell, we're going to have sodium moving in the opposite direction according to active transport. So here's our sodium-potassium pump. Sodium can leak into the cell freely and then be actively pumped outside the cell. And that will basically keep the cell at steady state so that there's no accumulation of sodium on either side, because that's going to be dangerous, right? We want to maintain a set number or a set level of sodium concentration on the inside of the cell and a set level on the extracellular fluid, and that needs to be maintained. So sodium can leak into the cell and then actively pumped out, and that will keep the relative concentrations the exact same. Same thing goes for potassium. Potassium can be actively pumped into the cell, and then there are leak channels for potassium to freely dissolve outside the cell as well. Again, this coordination of pump versus leak, that is what keeps the relative concentrations of the ICF and ECF the same. We can also think about the glucose carrier as another example. The glucose carrier or transporter is going to be on the basolateral surface of this cell. It's going to help us uptake, take that glucose that comes into the cell. So glucose moves into the cell according to the sodium glucose cotransport, right? So this is secondary active transport based on what we described earlier. So sodium comes in freely, and coupled to that is glucose coming in against its gradient, using the energy from this movement of sodium. So glucose gets into the cell, and because we need it to get into our bloodstream so that we can circulate it, we have to move it across the basolateral membrane. So this is where the glucose transporters come into play. So glucose is going to move according to facilitated diffusion here, which is an example of passive transport. Remember, this is a green arrow. So high glucose concentration inside the cell, low glucose concentration out here. And so glucose can dissolve down its concentration gradient into the bloodstream. So this is how we can have a combination of all the different types of transporters, channels, pumps that we have talked about, and they're all working together on different parts of the cell membrane to move these molecules from the lumen into the cell and then eventually to be absorbed into our bloodstream. Okay. If we look at the sodium transport, so I basically described this earlier, so I'm going to skip right over this part. We talked about this as well. So the secondary active transport, which brings glucose in actively, and that is coupled with sodium moving in passively. And then we talked about the concentration gradients for glucose. So the prompt question here is, in this scenario, where is the glucose concentration higher, ECF or ICF, right? And so basically, because of the passive movement, we know that glucose is higher inside the cell. So there's less glucose in the lumen, more of it accumulating inside the cell. So glucose has to move into the cell across the apical surface actively. Whereas because there's a higher concentration in the cell versus a lower concentration in the blood, it's going to move across the basolateral membrane passively. All right. So we can already begin to think about a low glucose in the lumen, low glucose in the blood, and then high glucose in the cell itself. Now, the last thing I want to just introduce here is the solute movement according to water. So solutes are always going to move and then water will follow. This is why it's so important to think about solute concentration as well as the water concentration gradient, and think about how solutes are pumped and then water can follow that gradient, right? Wherever solutes move, that shifts the water gradient, and therefore the water will move according to that solute change as well. So the osmotic pressure that is created by changing the solute concentration, remember, we said that the osmotic pressure is the ability for solutes to pull water to them. So the side of the membrane that has a higher solute concentration will effectively pull the water in that direction. So because the body knows this, and because this is an efficient way to create water movement, it can just pump solutes in different directions, right? If I have pumps on the membrane here, pumping solutes out, so solutes are moving from the inside of the cell into the interstitial fluid here, which is the fluid around our tissues, guess what? Now we have a higher solute gradient on the interstitial fluid area and a lower solute gradient out here in the lumen. And so now water wants to flow from the lumen into the interstitial fluid. This is how we absorb water into our tissues. This is how we keep our tissues moisturized and, hydrated, by creating solute gradients first, by pumping solutes into this area. And then because water really wants to get to this area of high solute concentration, it will naturally flow by osmosis to this area.